Alright, this is my third attempt at recording. I just had my wife burp while drinking a tea. And she's trying to hold her laugh in. What an intro. Least squares regression line worksheet, arithmetic method. I'm going to show you a few examples in regards to significant figures. And then with question 4 onwards, I'm just going to show you question 4 and 5. A lot of people assume that question 4 onwards, you can just use your calculator, specifically the statistics part, to work it out. But because the title implies that we're using the arithmetic method, there's a certain set of formulas that you will need to use in order to answer this. All you got to do is plug in specific numbers into the set formula and you can obtain the information required. We'll get to that in a second. For now, let's have a look at significant figures. So how many significant figures is each of these numbers written? The thing about significant figures, it just depends on whether the number is decimal or not. And if it is decimal, if it has any leading zeros. And if it's not decimal, if it has any trailing zeros. So what do I mean by this? Look at the first question. In this case here, we know that every single number is non-zero. So regardless of whether there's a decimal point there or not, we know for a fact that there are 4 significant figures within here. The second one, it gets to a point where anything after the decimal point here, we have to consider whether these are significant or not, but it also depends on whether this number leads with any zeros. Because this number leads with a 9, anything, and which is a non-zero number, anything after that decimal point is considered significant. Okay, so in this case, this 9 is significant, and as a consequence, after the decimal point, everything is significant afterwards. So 1, 2, 3, 4, 5. There are 5 significant numbers. This third question, C 500, no decimal point within here. So the 5 is considered significant, and then any non-zero numbers afterwards becomes insignificant or not significant if they just keep trailing on as zeros. So in this case, there's only one significant number, okay? And by significant, we just mean that it holds some form of importance, depending on the context of what we're talking about. These zeros here, they're still important numbers, they have their place of values, but they're insignificant depending on context. It's like saying, oh yeah, we scoped out how many people were at school today. There's roughly 500. That 5 within that 500 is what's significant and would make the difference between 600. Those zeros in between, they're just insignificant. Okay. This one here, it has a decimal point, but because it starts with a leading 0, any zeros after that, after the decimal point, are also considered insignificant. So this is insignificant, this is insignificant, this is insignificant, and then the 8 onwards becomes significant. So there will be 8, 2, and 5, which is 3 figures here. And so you can see there's a difference between this one here and this one here. Because this led with a 9, which is a non-zero number, those zeros here are significant. But because this leads with a 0, any zeros after that are still insignificant. Okay, takes a bit to get your head wrapped around it, but with enough practice, you will get the hang of this. 25.9 is the easy one. 3, 11.0672. So see how there is a 0 regardless of these numbers here, because they are non-zero numbers leading. All of these numbers here are significant. So the 1, 2, 3, 4, 5, 6. 34.0200. Now you see how these end with zeros? It's safe to think that it's only 1, 2, 3, 4, but because there is a decimal point here, they are considered as significant. Okay, so this is 1, 2, 3, 4, 5, 6. And the last one, leading 0, leading 0, leading 0, even though this is a decimal point, 4080. In this case, there is 4. So 45133664. Complete the following table. In this case, we want to round this number to either 5 significant figures, 4 significant figures, or 1 significant figure. I'm going to go ahead and pause this video, and I should have all the solutions readily available. Alright, here are the solutions for this one. Just making sure that when you do your significant figures, that you're not just forgetting the amount of numbers, especially for non-decimal numbers, how many numbers there are. So this particular case where it says 5 significant figures, for this one here, we're going to count 1, 2, 3, 4, 5. So these are the 5 significant figures. We don't just get rid of that 2, it actually just drops down to a 0. Okay, so this is saying that these 5 numbers are significant within here, and that 2 place value pretty much is insignificant or redundant, so we just put a 0 there instead. Okay, for 4 significant figures, it can only be done as 3, so we count 1, 2, 3, 4. But because when we write that 0, all the numbers afterwards also become 0, they become redundant. It doesn't get rounded to a 1 because this is a 4. Everything else turns into zeros. We can only round this to 3 significant figures. Okay, so a bit of a trickery to it. Now with this one, again, I'm going to go ahead and fill this in. We're looking for the number of significant figures, which will count as n for each of these expressions. So you'll get 2 numbers and or 2 figures, and the amount of significant figures within there will be the same between the pairs. We're going to get an unrounded answer, which I'll use the class-based calculator, and then I will get a correct answer to n significant figures. So what we've worked out here, in this case, there are 3 significant figures for each of them. When you have an unrounded answer, you get this, when you just multiply those 2 figures. But then when rounded to 3 significant figures, this is your answer here. Again, I'll go ahead and pause it, and you should get solutions. Alright, so we should have 4, 2, and 3 for each of these figures of number of significant figures. Unrounded answer, which we got from the class-based calculator here for each 3 of them. And the answer is correct to that amount of significant figures found. So here we've got 4, 1, 2, 3, 4. Here we have 2, so it's just 1700. All the numbers afterwards turn into zeros, and we just drop all the numbers after the decimal point. And 55.2, as 3 is the number. You notice here there is a power. That power isn't part of the figure. It's just saying it's 7.43 multiplied by 7.43. So we're not including this 2 as a digit. It's not a digit, it's an actual operator. So just be careful when you get questions that look like that. Now we're going to have a look at the questions that I'm assuming that a few of you had trouble with. And it's to do with using the arithmetic method to get the values of A and B for the regression line, and try to figure out the what it is that you need to do to get these values. So we're used to using the statistics part of our class-based calculator, provided that we have the statistics there in front of us. We have all the data points. In this case, we don't have those data points. We're only given 5 sets of information. 2 means, right here, 2 standard deviations, which I'll explain what a standard deviation is in a general sense, and we have those 2 here, and a correlation coefficient, which is also known as Pearson's correlation coefficient, R. And all you need to do is plug in these digits into the following formulas. And I'll get to that in a second. For now, let's look at the context. The study was conducted to find the relationship between the height of Year 11 boys and the height of Year 11 girls. The following details were found. The mean height of the boys was 182 centimeters. So mean is just the most common way of getting the average, adding them all up and dividing by however many there are. In this case, we don't know that information. All we do know is that the answer ended up being 182. The mean height of the girls is 166. The standard deviation of the height of boys is 6.1 centimeters. What is standard deviation? Standard deviation, all that means is the average of the spacing out of each data point. So on average, if we were to get the heights of each boy, and we get them from shortest to tallest, and we have all these, we don't know how many there are that are there, but they're all lining up, and here they are all standing there, and some of them short, and then they eventually get taller and taller, and they keep, so this is a shocking example, but they ended up getting to the tallest person. The standard deviation just means the average spacing between each of these students, specifically boys, is 6.1 centimeters. So this is just an average. So there might be some bigger spacing between a few students. There might be some smaller spacing between some students. But if you were to get the average of each of these spacings out, you would get 6.1 centimeters. And so the standard deviation of heights for the girls being 5.2 just means on average, the spacing out is just slightly smaller, almost a centimeter, nearly there. That's all that standard deviation means. And to deviate just means to get yourself away from something, which is what's happening within here. We're looking for the standard or average amount. And the correlation coefficient, the R value, is 0.82, meaning that is somewhat of a strong correlation between the two. So now that we've got that information, the form of the least squares regression line is to be in this format. To find out the height of a year 12 boy, I'm assuming that's meant to say year 11 boy, not year 12. To find the height of a year 11 boy, let's be consistent here. This is going to equal some value A plus some value B times the height of a year 11 girl. And the first question is asking, which is the explanatory variable? Now, if the format has been given to you already, this is actually quite simple. The explanatory variable is always the one on the right-hand side of the equal sign. This here, the height of a year 11 girl, will explain, the height of a year 11 boy. So the height of a year 11 girl is going to be the explanatory variable. This is the one that explains the other thing. Now, in real life context, there's no way that this can be realistically done because these two variables are quite arbitrary. One's not necessarily going to explain the other in a real life context. Maybe if there was some form of association or correlation between the two, but for the sake of this example, whenever the template has been given to you, this one will always be the explanatory variable, meaning this one here will be the RV or the response variable. Okay. The response variable is always going to be the one that's by itself. It has no letters associated with it. It has no A or B or whatever these digits are. Okay. So the height of the year 11 girl is the explanatory variable. Question B says, calculate the values of A and B for the regression line to the four significant figures. And this is where we use this arithmetic method which was found in one of the previous exercises in chapter 7. And all we're doing is we're simply finding what b is by substituting the values into here, and finding what a is by substituting the values into here. You can't find a without having to find b first, because b is used in the formula for a. Now, I'm not going to get into how or why these formulas work. There's a lot of maths involved. All you got to know is that they do work. You've just got to put in the required values. So to get our b value, I'm going to write the long notation out. So just including the multiplication sign. This is saying that b is equal to our correlation coefficient r, which was given here, multiplied by the standard deviation of y, s being standard deviation, and the subscript just meaning that little part of it on the bottom right of it of y. Now, what's the standard deviation of y? We've been given two standard deviation, and it doesn't specifically tell us which one the x one is and which one the y one is. But what we do know is that the height of a year 11 girl is the explanatory variable, meaning it is the x value. So the standard deviation of height of a girl belongs to x, because it is the explanatory variable, meaning the response variable is the y. The standard deviation of the height of a year 11 boy, and this is the response, meaning it has to be the y. So we know what our sy is, and the s of x is here. We can go ahead and plug these values in. So our b is equal to 0.82 multiplied by s of y, 6.1, all over 5.2. Once you know what these values are by finding your explanatory variable, it's just a simple case of substitution. It's knowing what you need to substitute and knowing that you have to use these formulas. That's the tricky part. So let's go get ahead and get our keyboard out, put into the fraction form right here. 0.82 multiplied by 6.1 all over 5.2. This is going to be equal to 0.9619 230769. Now, I'm not going to actually put this solution. No, I am actually. It's going to be to 4 significant figures, I believe. 0.9619. There's my 4 significant figures. That 2 is lower than 5, so that 9 is unchanged. 9619. 9619. So we have our b value. Okay, so the b value is the thing that gets multiplied by the height of the year 11 girl, which is also considered as the slope. I'll just put that here. This is the slope. And now we're going to use that b value to get our a value. So a is equal to y dash minus bx dash. Now what is y dash and x dash? Y dash just means the mean of y, and x dash just means the mean of x. We already know what the mean of each of them are. The mean height of the boys is 182, and to do with the boys is the responsive variable. So this is y dash here. Should write s of y here and s of x here. Meaning this one here, the mean height of the girls is x dash. So now with this in mind, we are going to plug in those numbers to get our a value. So y dash 182, so a is equal to 182 multiply that by, and I put these in brackets, our b value 0.9619 times our x dash value, which is 166. Go ahead and let the ClassPad calculator work this out. 182 take away 0.9619 multiplied by 166. This is going to be 22.32. 22.32, 4 significant figures. So we've calculated the value of A and B for the regression line, meow and meow. And what we're going to do now, and I'll wrap it up after this explanation, is we're going to write out the least squares regression line. But we already know that we've got the template for it. We're just going to replace it with our A and B values. So height of year 11 boy is equal to the A value that we got, 22.32, plus, there's a plus. We know it's going to be a plus because the B value is positive. If it was a negative, it would be a subtraction. And this is 0.9619 times the height of year 11 girl. Height of year 11 girl. And I'll leave it here. So just a summary, make sure you use this arithmetic formula. I'll actually find out which exercise that's from. If you go ahead and check out your lesson 6 notes, exercise 7F, using least squares line to model a linear association, it can be found here. And another note is just knowing what y dash, x dash, s of y and s of x mean. That just means standard deviation for y and x, and the mean for y and x, which the question will be providing you. You just go ahead and plug it into those formulas, and get your explanatory variable, and use it to find your A and your B. And another thing is this here, I wrote it here as a slope. This here, this 22.32 is also the intercept. So if we were to get some context into this, actually I'll leave it there. I'm going to shut up now. 23 minutes, I think that's enough. Use the rest of the period to be able to answer question 5 onwards. Apologies for not being in, feeling quite unwell. I'll explain when I get back. For now, do what you need to do. See you guys soon.